let's just wing it and see. Right, cool. So we're looking today, like I said, lossless coding. Now, one of the things about lossless, as we talked about last week, the difference between lossy and lossless. Lossless is you can get back to a bit perfect, exact copy of something. So the key contention here is, how are we getting rid of stuff but keeping it the same? You know? And we discussed out last week, the idea of last week's little session bit that we did was to think, how can we do that? Maybe there's some ways of going about that. And I'm going to show you some of the ways. Again, this isn't an exhaustive thing. You could easily do an entire degree on this, and I say that about a bunch of the different things that we do. We tend to dip into all this stuff a little bit. But I'll discuss some of the stuff we actually do. And then obviously later on, we're going to start to discuss actual uses in media. And that's where lossy starts to come in, because in media, we can be lossy. But lossless coding, this is the same thing that is in the back, in the systems that do everything, like encrypted, compress stuff. When you compress your hard drive, it'll be using these techniques. If you use a zip file or anything like that, it'll be using these techniques. Inside JPEG and inside other media files, they will be doing lossy compression, the stuff that we'll learn about later, but they'll also be doing this. This is like a freebie. The only thing this costs you, or the stuff we're about to talk about today, is time. When you click a zip file, it's got to have a little bit of a brain fart before it flings all the stuff at you. And that's essentially what you're trading off. You're throwing computer cycles at it and RAM and all that kind of stuff. Stuff that we've got lots of these days in order to make your storage smaller, or you sending something across the internet or whatever. Whatever the thing is you're doing with it, your actual size of the object smaller. And again, a lot of the things that we do in this module, or during these concepts, is to try and find out where we can make those decisions. One of the reasons why we're using better compression these days than we used to, and again, we'll see this through MPEG and JPEG and stuff like that. We've got stuff that's better than MPEG and JPEG now. One of the reasons we can use those is not because we've suddenly thought up amazing things and we've really conquered technology in any better way. It's just because processors are faster. So the faster processors are, the more we can get away with stuff. And it's better and better for that reason. So today we're going to look at lossless. How can we reduce data but keep it the same? And there's a bunch of these, right? So we started to look at last week the idea of optimizing different things. And you said, well, maybe we could take a chunk of something. And if you see that a lot of times, we'll do it over and over again. And there's a bunch of other ways of doing the same thing. So essentially, the things we're going to spin through today: symbol optimization, so symbols being the characters that we're dealing with. We'll often use examples where we're talking about text, but obviously text is not the only thing. It could be pixel values. It can be any kind of data, all kinds of different stuff. So we often use text, but obviously it can be anything, numbers, pixel values, literally any kind of data. And where it can be any kind of data as well, another point here is we have to use different schemes for different things. As we'll see in a moment when we're talking about redundancy, when we get to that point, we'll start using dictionary compression, which is essentially having a big scheme where you can apply a number to a bunch of stuff, and you can describe a whole big thing with a single number. That works really well if you've got repeating sections. It works well for text. It doesn't work very well for JPEGs because the pixels are just a little bit different all the time. So there's lots of different kinds of data, and we will make different compression choices depending on what we're trying to do. So first one we're going to look at is symbol optimization. And I kind of alluded to this last week as, again, we started talking about, we started off with text like we always do. I said that we can take whatever the primitive is that we've got. So we said if we've got characters in text, I said that even with using ASCII or Unicode 8-bit, Unicode 8, it would be quite a big thing. It would be quite a big unit, and we can get rid of the first bit. So if we have ASCII, we've got 8 bits there. If we're only encoding a certain amount of characters, we don't need all of those. We can have a smaller amount of bits, and we can encode just the characters we need, for instance. And we're going to look at a scheme that allows you to do that in just a moment. But also, you've got to think in code, right? This is why we do code last year and thinking about primitives. The different primitive variable types. Whenever you ask for a primitive in a coding language, it's not designed to be small necessarily. It's often designed to be compatible and fast in order for coding, right? So just jump to the bottom here. The quick example here would be this. This is the number sequence, right? 9, 11, 11, blah, 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 this number sequence. It goes up. You can see that none of it gets to a particularly high number. But if you ask and stored that in an integer in a programming language, the default thing to do would be to give you a 16-bit or a 32-bit integer. So if you did no compression to that and just stored it, those numbers would look like this. And you can see there's a lot of redundancy in there. There's stuff we don't need, right? So we can decide this stuff. And again, we're not looking at any particular implementation here. We'll look at some implementations a little bit further down the road in this lecture here. But acknowledging that there's stuff that we can do there, the very basic idea that there's something we can shorten there. So integers, like I say, most of the time they're 32-bit. So if you are using Python, for instance, as your programming language, you say, I want an integer, it will by default give you a 32-bit integer. So that can obviously be slimmed down a bit. Floats are the same. By default, they're 32-bit. If you ask for a double, which is the double size one, you get a 64-bit float. Characters, again, it'll be Unicode 8, Unicode 16, maybe even Unicode 32. So you're using a ton of bits there. Maybe you don't want to. And strings are literally characters, but then lots of them. So that is obviously massively wasteful if you're not careful with that. So first concept then, we can optimize symbols. That's quite clear, hopefully. You can take your symbols, you can come up with a new scheme where you're not quite so wasteful with them. Secondly, if we look at the same numbers again, I thought I'd put them on the screen, but maybe I didn't. Yeah, they're supposed to be listed at the top. These are these same numbers, by the way. So when you see the next bit, number sequence. So instead of actually sending those individual numbers, perhaps instead we can do something predictive. We can say, right, well, I can predict what's going to happen next. And instead of just sending, if this is a stream or if this is a, some sort of bit stream that's happening, instead of just sending the whole number every time, maybe I could just send the error. So if this was perfectly predictable and they were on a perfect line and we could use a Pearson's coefficient and it would be a Pearson's coefficient of 1, so exactly just a number, and it would all slot exactly on that line, then we could go ahead and say that we would have next to no error. And if it's a very, very predictable thing, those error numbers will be very, very small, and therefore we're sending small numbers and saving data. So this, I haven't done it because I didn't want the hassle of it. We could put a trend line on there, essentially. That's our predictive line. And instead of actually sending the discrete numbers, there's the number sequence, instead of sending each of these discrete numbers, which can be tens, we might just send single numbers, which are just the errors instead. We'd have to account for positive and negative numbers in that scheme somehow, but again, we're not into implementation here. We're just thinking broadly about how we can fix this thing. Now, as a spoiler, this is kind of how MPEG works. You look at a frame, and then instead of sending a whole frame next time, you just send everything that's different. So you can just send errors, which is a nice way of getting a bit of, well, quite a chunk of compression. So we can establish trends, and we can look at predictive coding, so coding a difference. We could do something like a statistical method, right? So again, it's quite natural to establish the idea that language has words, which is quite useful. So language has words. So instead of coding every single character, or maybe as well as coding every single character, we could just assign a code to a specific common character. And we'll actually see an implementation of that in just the next slide where we actually do this. So the idea there, we can take statistical information from our data stream, whatever it happens to be. And again, text is a good example. And I stole this example, which is why it's a weird one. It's like a Baryan array ran this thing. So that is obviously got a lot of redundant characters in it. A is used an awful lot, basically. So here we could encode, we've got 8 symbols, which means that we'd need 3 bits to encode that. But if we were using a set number of bits, if we use a variable rate instead, we can code it with a smaller number of bits for the more common characters. So the more common characters, you end up with smaller a number of bits, as long as the system knows about that, and that's the tricky thing, right? It understanding when the characters begin and end is the tricky bit. But as long as it knows that, you can encode that in such a way that you have the same number of bits on average, or a smaller number of bits on average ideally, and your more common characters, which in this case are A and the space character, with a smaller number of bits, and therefore you end up with a compression. And whenever we talk about compression, we talk about a compression ratio. So in this case, instead of 3 bits, you get an average with that particular example of 2.58 bits per symbol, because those bits are changing in size every time a character is sent. So you end up with having to describe its average, which is a compression ratio of roughly 1.16 to 1. Yeah? Now, that's difficult to do, isn't it? Because if we think about that, how do we decide for any given message which symbols get the shorter codes? How do we decide what that code looks like? And how do we decide, on the other hand, or the other side of the transmission, whether it's opening a file or transmitting and receiving a bit stream, what those ones and zeros represent? Because we have to remember that those ones and zeros are just going to be like a pipe. We're just going to be pouring them at something, and it has to take them all and understand what they are in their own context. It has to say, right, that 1 is an A. That's the reason there's a 0 at the beginning of all of there, by the way. This is a slightly more workable scheme. So they have to be unique in the sense that when it sees a 1 on its own, it needs to know that it's, when it thinks it's going to interpret a new character and it sees a 1, it needs to know that it's an A and then move on and not expect any other symbols. Now you will see that in this scheme, we are using more bits in certain circumstances, because we have to make these understandable on the other side. Like I say, they have to be unique sequences of code. You can't have subsets. So I can't have 001 and then follow that with something, because otherwise it won't know whether the character's finished or not. So there are some things you have to give up to get that scheme to work, but it does work. You have to be careful and clever about how we do this. So this is statistical redundancy and using a variable length coding scheme. So variable length meaning we have different number of bits, and it's statistical in the sense that we try and code the more common characters with fewer bits. Now Huffman coding is the way in which we do that. The great thing about this is that, I've not written it somewhere in a page or two, this is optimal. We don't really get that very often. Usually you think, oh, we can totally improve that somehow, and it feels a bit like this or that, but we can improve it, or maybe someone coming up with a new technology or a new scheme. This is mathematically optimal. So the thing that we're about to see here, for single characters, you can't compress any better than this. So we've reached, for lossless, we've reached the apogee. So this was a guy called David Huffman, did a bunch of stuff in computer science, and this is where, this is why I'm so keen on computer science and you guys to learn a bit of it, because it comes back into our world quite a lot. Like, we're not far from computer scientists these days. Came up with this scheme called Huffman coding, because if you do something this clever, you get it named after you. And essentially it's like a table structure that enables you to encode any format, any data format. So interestingly, and this is the reason I put this bit of history here, this guy was set this, I can't remember the university, but it was by a guy called Robert Fano, I don't know who that was, and Claude Shannon. And if you remember from the Nyquist-Shannon theorem, it's the same guy. So, these guys, Shannon and Nyquist were the first sort of information, what do they call it, communications theory specialists. This was a new field that they basically coined and made themselves. So the idea of sending things in digital world in the 50s was new, and they were the first to do that kind of, really conquer that area. Things like the Nyquist theorem and this and other things were all being invented at that time. So Huffman coding, massive outcome, prolific. So any given computer in the world probably uses it. It's massive. It's one of the fundamental foundational things that we use. So we're going to look into it a bit today. And this afternoon, you're going to fire up the computers and, and have a look at making a Huffman code, basically, for a string of text. Nothing too complex, because we'd be here forever. Obviously, we get computers to do this for us so that it's fast, but interesting to know all the same. So this is based on 2 observations, and the original brief was kind of there, and they have formulated these observations based on the original brief. And the original brief was basically, how for any given message can we make sure that we squeeze it an optimal amount, or as much as you can? And lots of the students were doing their work and going around it, trying to figure it out. I think there was a bunch of PhD students that were together to do this kind of work. And yeah, so Huffman, there's some tale that he tells about how he was really failing at it, and then he had like an epiphany and it turned into a whole thing. But anyway, so the two observations were, in an optimum code, so in order for it to be optimum, symbols that occur most frequently will have shorter code words. That makes sense, doesn't it? Than the ones that occur less frequently. And the next one, a little bit less understandable. In an optimum code, the two symbols that occur the least frequency will have the same length. So what he's kind of saying now, what they're kind of saying with this brief here is that you don't want the very least ones to have a different length because that means you're using an entire extra bit, I think is the point there. You know? So if your least optimal code, like the one that's the least occurrent symbol, happens to be 5 bits, you also want the other one to be 5 bits as well. You don't want to go to an extra whole bit for the sake of one extra character, otherwise it's not optimal. And as a spoiler, as you might see in a moment, these aren't always the same. You can make valid Huffman tables or Huffman trees that will describe the same data, but they can look different, have different structures. So they aren't mathematically the same, but if you construct a valid one, it's mathematically optimal. So just to be clear on that, if you have two different Huffman schemes and you've got a different algorithm running on each end of your transmission scheme, it might fall over. So it's not, you know, it's an algorithm that you will design based off this. So this is a Huffman tree, right? So this thing here, this is what it looks like. Seems really unintuitive, crazy stuff going on at the moment. Well, I'll explain it, hopefully. So we're going to build that tree. So here is an example. So the tree itself, the thing you saw, obviously corresponds with the frequency of occurrence of those letters. The common ones you want to be right at the top, and the least common ones you want to be down the bottom. So the common ones are really easy to get to via a few of these nodes that we're looking at here, and the least common ones have got to be down in somewhere else, and we can grab them every time we need them, right? So here we've got we're going to encode this piece of text, abracadabra, all as one word, and obviously it's chosen specifically because it's got a bunch of A's in it. And so the first step in the process is to look at the letters and count the frequency of them. So you can see we've got 5 A's, 2 B's, 2 R's, 1 C, 1 D. Abracadabra. Now we're going to start building the tree, right? So each of these decision points as we go up and down the tree is called a node. Each of the letters has to have its own node, otherwise you can't get there. And each of the nodes on the way, we call them, they've got various names, calling them intermediate nodes here, or pathing nodes, so the nodes that allow you to get down to the letters. So if we go back to here, look, you can see that the letters are down here, and we have to have these pathing nodes that get us there. Otherwise we can't access them, right? So that's the key thing. So every single one of them's got to have every letter has to have a node that just describes its letter or symbol, could be a symbol. These could be strings of, well, I shouldn't say strings, but you know, words, binary words, anything. But we use letters to keep it simple. So we start to build the tree. Now, I've done this upside down because I think it's easier to understand. But when you actually look at Huffman algorithm, they start from the least significant bits, the parts, this bit here. I've done it from that side because I think it's easier to understand to go from the top. But just bear in mind, the actual algorithm starts from the bottom. Okay. So here, what we're going to do is we're going to say, right, the most common character is going to get its own node. We want that to be the shortest code. So in this example here, we're going to say, right, it's A. It's on its own, right over there. And all the rest of the nonsense, the other 4 letters, are going to get an intermediate node, and that's going to lead somewhere else, and we'll work that out in a moment. So the next thing we do, we go to the next most common into another intermediate node. We need to limit the depth of this tree as much as we can. So we want as few stages as possible with unique codes for each letter. So what we do, we've got an intermediate node here with 4 letters in it, and we've got 4 letters here. So the natural thing to do would be to break them into 2 twos. So we're going to put B and R together, which has got this. This is the next most common combination, gives us 4. And then the next most common combination would give us that. We can have that deeper in the tree if we need to. So from this point here, we can decide which way we're going to go to get to our letters. So we've got B and R or C and D. They go in one of those two different directions. That completes all the symbols. Now we need to have individual nodes for each of our letters. So here we can see, if we're coming down the tree here, we're going to say, right, we need, for instance, the letter B. So we're going to have to come to here, then we're going to have to go to here, and then we have to go to here. So it's a number of hops through the system. That number of hops corresponds with the number of bits we need in order to describe it. Okay. So now we've got all these symbol nodes on there. Does that kind of make sense so far? This is a bit sort of, almost feels a bit random what we're doing at the moment, but hopefully it'll make sense in a second. So we fill out all these symbol nodes, and we've got everything we need there. We pop one at the top, which is basically an intermediate node that says the whole message. So the whole message is going to be A, B, R, C, D, and then we can make decisions from that point onwards. It's the first decision point, essentially, so it's the first intermediate node. That completes our Huffman tree. Okay? So from the top there, we can cascade down that, and eventually we'll find every letter we need. Yeah. Now, this is where the magic comes in, and this is why it's clever. Every time you go left, you code a 0. Every time you go right, you code a 1. So in this scheme here, you can say, well, we're going to branch down, and every time we go left, we'll code a 0. So the very first Huffman code is the most common symbol, and that's just A, gives us a 0. Every time we go right, we code a 1. So it would be a 1. So if you wanted to get to B, for instance, it would be 1, 1, 0. Like that. And the beauty of this, I'm not sure that is actually a legit Huffman code now that I look at it. Is it? Might not be. Either way. The beauty of this is that we can build one of these as we go for any given message or combination of ones and zeros we want. And that will allow us to make a perfectly mathematically, perfect, smallest we can get it for each of these individual symbols on the way. So this is the way in which this actually happens. So you basically have the same algorithm at both ends. So either it's saving and opening a file, or it's sending something and receiving it. And what you do is you have that same algorithm that codes the Huffman tree. The other side has to receive the Huffman tree, so it has to see this thing. So you have to encode it in your file. And then when it loads it up, it uses it to basically break it back out again, uses the Huffman codes in order to get all the symbols back out, and it decodes the message. So this is great for text. This is great for, what is it great for? It's great for everything, really. You can put Huffman coding as part of any compression scheme. And those codes can be adaptable to what that message is. That's the key thing about this that makes it so important. So you could code text, and that would be really good because all those letters that you've got in the English language would be nicely coded through this. You could code DNA, 4 characters, 4 different symbols. It would code that perfectly well. Any single thing that you want to put through here, it will make a mathematically perfect shrinking of it, basically, for single characters. Okay, so it's quite clever. Now, if we look at what we've done there, again, this is a method of doing symbol redundancy, essentially. You've got abracadabra there. We've done it in Unicode 8, so you can't really see the spaces there, but there's a character each side. So there are 2 columns of characters there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that would be what it looks like. If we were just send that in Unicode 8, obviously a bunch of characters there. And if we were going to send that in Huffman code, well, it would be 88 bits. If we were going to send that in Huffman code, it would be a mere 23 bits. Quite good. So we can actually encode that stuff down really quite well with it. It's quite clever. Now, I say, the only disadvantage is we have to send the Huffman code with it. Now, in a file header of a JPEG, it will send the Huffman code. You can actually take apart a JPEG and look at the header of information, and the Huffman information will be in there and how it's coded together. So you have to actually send that. So it doesn't really work particularly well for very small messages. Stuff like this, these like little examples, abracadabra, etc., it doesn't actually work very well for, because by the time you send the Huffman code, you've lost all your compression. But just be aware, it's a very useful thing. You typically save about 1/3 of your data using this, depending on the message. So that's quite useful. Now, what does it not do? What's it not doing? we're encoding all these different symbols. Any guesses as what it's not very good at, or not doing at all?
Numbers.
You can do this for numbers as well. It's a good shout, but yeah, you can do this with numbers, and you can do it with like combination of bits as well. What it's not doing here is combination of symbols. Like if you were going to send something that's text, for instance, it would be really good if you could just encode the, or space, because that's always what you see. You never see the with a full stop afterwards, so you might as well put the space after it as well, right? And then you could make a system where you would encode a very short code for that, because you see it all the time. So this is part of a scheme. Another part might be redundancy finding using dictionary coding. And that's what that is, basically. So statistical analysis of individual symbols helps you encode single symbols, and it will help you encode instances where you've got the same letter lots and lots of times in a piece of text or something like that. But language and other data types as well has patterns. Like patterns are very common, which is why if you have things like bitmaps and things like that with recurrent patterns, the compression is better because it uses essentially a dictionary building system. So common words, phrases, anything we like can be encoded as bit sequences. You could put the entire works of Shakespeare into a single bit if you wanted to, but that wouldn't be a very adaptable compression scheme, but it'd be a very efficient one for that particular thing. But we have to kind of scroll that idea backwards and forwards depending on what we're trying to send. So you can make a dictionary code. You can actually make a dictionary code in the real world as well. So if everyone's got a Collins 23rd edition dictionary, you can do this. A good example of how a dictionary-based compression works, you can say, right, on page 1, it's word 1, which is that one. On page 822, it's word number 3, which is that one. And that actually lowers the number of symbols you're sending. You could do that. If you were just coding an integer, you wouldn't have to code all of ASCII, and thereby you would actually make smaller, it's a compression system. So page number, word number is an example. It's almost like a meta example of a dictionary coding scheme. So that's one way in which we can do it. We do it in person as well all the time. I put the example in the first, that's why I wrote this stupid thing at the top here. So the idea of having contractions, can't, won't, shouldn't, isn't, those are dictionary coding schemes. We've saved letters by all just agreeing we know what happens in the middle there. Like a lot of them aren't very efficient, obviously. We could just put a zero in there, an O in there instead. But you know, it's something we do. It's a dictionary coding scheme that's gone into the English language, and it's just a thing that we actually use. There's another really good example of a dictionary coding scheme. One of these. Like, you've ever gone into a Chinese restaurant and be like, I'll have a number, whatever. What would I have? Salt and pepper chicken. Have they got that on there?
Salt and chili chicken.
Hell yeah. Salt and chili squid. I'll have a number 2. So this is an example of a dictionary coding scheme, right? So they give you the dictionary of this, and you phone it up and say, I'll have a number 19, whatever. So another good example. However, obviously these things are not very useful generally. They are very unadaptive. And there is a really cool dictionary coding system that is very adaptive and is adaptive to any, again, it's useful to have these things in computer science. They're adapted to any kind of system or any message. And LZW is the one, Limpel Zev Welch, or Welch, Limpel Ziv Welch, is that exact thing. So Limpel Ziv Welch is a dictionary coding scheme where what we do is we go through, and every time we see a new character or a new combination of characters, we code it. So it's a fixed length code. We decide on the size of the thing that we want. And then we basically just run through the message. And every time we see something new, we look at the next character along and code that. So an example of that would be if you go through a message, say maybe the message is a space message as a message. So the first thing we'll do is we see a capital A. We'll put that in our coding scheme because we need a way to say what it is. The next thing you would do is go along, and every time you get a new character you've not seen before, you store it. Every time you see a character you've seen before, you store it and the one next to it, and you just basically keep going like that. What that does is it keeps rolling through, And if it keeps seeing the same thing over and over again, the thing that it's storing over and over again gets larger and larger and larger. So you run through a message, and if it's got commonalities in it, it will constantly store the larger thing, larger thing, larger thing. So if there's whole sentences that are the same, by the time you've gone through the message a couple of times, you'll be storing the whole message, that whole sentence, as a small 8-bit character representation or something. Now the cool thing about this is it only stores the characters you're using. That's quite good. You can pre-seed it by just giving it the entire Unicode 8 or ASCII character set to begin with. So it doesn't have to go through and code every single English or Roman letter as you go through. So you can pre-seed it or you can just let it do it. It goes through and scans it, and every time it rolls over it, it encodes the binary for each of those. So every time it finds an entry it's seen before, it will add the letter next to it and then add that to the dictionary. And as you go through a long and complicated symbol of a bunch of ones and zeros or letters or characters or whatever, again, they're always using characters of a sentence to demonstrate this, but more often than not, the computer will be doing it with combinations of ones and zeros. So if you think about it, it sees a 1, it stores a 1. It sees a 0, it stores a 0. If it sees 0, 1, it then stores 0, 1. And every time it sees that, it's shorthand. And then if there's a long set of characters that's 52 long, every time it sees that, it's a shorthand. You can store that in a short code. Now, there's a lot to that. It's probably quite confusing me talking about that. So there's a video. What I stole off YouTube.
Channel. If you were to take a look at
Do we have any audio? Every time you try and do a video, the audio doesn't work.
any data.
And then it's too loud. Okay, let's try that again. So we're just going to play this from the beginning. Like I say, it's just the first start of this video because it explains it in a much better way than I could put animations together for, basically.
The advantage of the additional pulses with C2 Plus in treating kind of diffuse calcium that has eccentric and maybe nodular calcium mixed in there gives you the opportunity to treat it entirety with usually one balloon, because what you can do is do a couple pulses where it's kind of that diffuse or eccentric calcium, but when you come to the nodular areas, you can actually lay on it with a few extra cycles, anywhere from maybe 20 or
whatever.
If you were to take a look at almost any data file on a computer, character by character, you would notice that there are many recurring patterns. LZW is a data compression technique that takes advantage of this repetition. The original version of the method was created by Lempel and Ziv in 1978 and was further enhanced by Welch in 1984, hence the LZW acronym. Okay, LZW is a dictionary-based compression algorithm, meaning that instead of counting characters and building trees based on that count, such as we did for the Huffman encoding, LZW encodes data by referencing a dictionary. Thus, to encode a substring, only a single code number corresponding to that substring's index in the dictionary needs to be written to the output file. This dictionary starts with what we call the standard character set, represented by the first 256 ASCII code characters of the alphabet you see in front of you, and based on the provided input, the algorithm proceeds by enriching this dictionary with additional entries. Take this input text, for instance, along with its starting dictionary, and let's try to encode it using the LZW algorithm. The first character we have here is the G, which is already present in the dictionary and represented by the code 103. Now remember, every time we find a match in the dictionary, we hold onto the character at hand and append to it the next character in the given string. So in this example, we hop to the next iteration and append to the G the E to obtain GE. Now, GE is not present in our current dictionary, so we create an entry for it, the 257th entry, then reset our iterating saved character to the current one only, which is the E, and finally append the code 103 to our encoded output. I know you're a bit confused, so let's proceed to the next iteration, and it will become clearer, I guarantee. Our next character is the second E of Geekific, which needs to be appended to the first one. Now EE is not present in the dictionary, so we add an entry for it, and add the respective code of E, which is 101, to the compressed output. After resetting the character to the second letter E, we append to it the K now, and do exactly the same thing we did with the previous characters all the way till we reach the dash between the two words. You see, LZW will need a few characters at the beginning to start populating and enriching this dictionary to use it later on in the provided text. And that is exactly what it is going to do when we reach the next repetition of the letter G. So, G is present in the dictionary, therefore we hold onto it and append the E. Now if we check for GE, we will find it, and because we did, we also hold onto it and append the second E. Here LZW will create an entry for GEE and add to the output the code representing GE. The more this particular sequence of letters occur, the more this algorithm will be able to represent them using less and less codes. The same is done for the remaining letters of the second geekific word until all of our text is now compressed. Now let's try to decompress this same output using the LZW algorithm. To do that, we will start off with the same dictionary we had, and we are going to make use of a very similar logic, but kind of reversed. Let me explain this. For each code number we have, we are going to check if this code is present in the dictionary. If it is, we hold onto it, check the one following it, and append their corresponding characters along with a new code to the dictionary. So, by the time we reach the code 256, a new entry for GE having a code of 256 will have been created in the dictionary, allowing us to identify this entry used by the encoder. Note that while adding new entries to the dictionary, you should only use the first character of your current letters alongside your previous set. So in this very iteration, GEE is added to the dictionary similarly to what was done while encoding. This method allows us to encode and decode without the need to provide to the decoder the dictionary created. It can work alone, and the only information it needs is the text itself. Contrary to Huffman, for example, where we need to provide the decoder with the tree created by the encoder. However, because of this, sometimes the decoder may...
Leave it there. It does get a bit more complicated, but we don't need to know that, I don't think. So do you see why that's quite useful? We can precede the dictionary with the characters we're going to be using, and then just send the message. You don't have to send the whole dictionary. The dictionary is built on both ends. And you can see that we're actually reducing the size of those characters as we go, which is great, which is what we're trying to do. But we don't have to send the dictionary with it, which kind of saves us even for smaller messages. The only thing we have to agree on is that we're both using this coding standard, and we have to agree that we're encoding using a certain set of symbols which are preceded in the dictionary. Kind of useful. Did that make sense what was going on there? I know it's a bit like we do this and then we do this, but you know. And then one of the frustrations with this, if you think a bit more broadly about what's actually happening in the computer, you're not necessarily using characters. So all of the examples we see, again, they're all in text. But if you think how powerful that might be, every time you use a combination of ones and zeros in a row, a big file is just a million of them. And so as you go through a big file, you get more and more compression every time there's a repeating set of characters or a repeating set of ones and zeros in there. Those ones and zeros can come from pixel values and all that kind of stuff we've talked about before, or vectors, or like motion vectors, and all this different stuff that can come about. And if there's a common one that keeps happening, you can code it down into a very small thing, especially if you've got like a massive bulk piece of data. So that very first example there where he goes through Geekify or whatever it's called, it's kind of annoying in the sense that he only goes through and sees that thing once, but obviously that would encode that entire thing, and then if you keep repeating it, you'd get that whole thing would be coded in quite a small dictionary entry. And this is how everything's coded. Like I say, LZW goes into all of the compressed file formats we've got, which includes most of file formats. Like we don't really have uncompressed file formats because of this, because it's so easy to do. All we're doing is spending some CPU cycles and a little bit of RAM to run through something, build a dictionary, and then pop it open. And that's how it happens. Like it doesn't cost you anything really compared to the massive amount of storage space or bandwidth and all that kind of stuff that actually does kind of suck and still sucks even today. Cool. Ooh, all the controls are gone.
Decoding it, we will encounter
Stop it.
channel.